Well, good afternoon, everyone. It's Sandy Flynn, Director of Alumni Engagement at Minds. Welcome to our April Lunch Bunch. It's wonderful to see you all today. It's a really nice crowd. I'm sure there's more to join in here. It's been a busy month on campus celebrating E-Days. And last night we hosted the Entrepreneurship and Innovation Showcase at the Beck Venture Center. We had over 200 in attendance with 50 startups sharing their ideas and vision. It was a very exciting evening. I see several faces on this call that were also there last night, so we appreciate you coming back. If this is your first lunch bunch, thanks for logging on and welcome. We love having new faces on each month. And of course, if you're a regular lunch buncher, welcome back and thank you for your continued interest and support. Today, we are excited to be featuring Quantum at Minds. What exactly is it and how is Minds involved? So very exciting topic. We have invited Dr. Fred Sarazin, Physics Department Head and Quantum at Minds Director, to help answer those questions. Colorado has become the quantum tech hub in the nation with a strong ecosystem of academic institutions, federal laboratories, and private companies focused on advancing quantum science and engineering. Dr. Sarazin will illustrate the concept of quantum and provide an overview of some of the exciting ongoing activities that Minds is involved with. As always, before we start, a few quick reminders. If you have a question, please feel free to use the chat or chime in and ask as we go along. Dr. Sarazin said he'll be watching the chat also to see if it requires an immediate response. But all of our Lunch Bunch programs are recorded and can be accessed on the Lunch Bunch page of our alumni website at weare.minds.edu. So if you missed one, want to listen again, or would like to share the program with a friend, visit this page to access the complete archive of recordings going back to 2020 when Lunch Bunch transitioned to a virtual format. And as always, if you have ideas for future speakers or topics we want to know about them, please contact me or anyone in the alumni office with your suggestions, and we'll do our best to make it happen. This was obviously a very popular topic, so it rose right to the top. Okay, let's get started, and please help me welcome Dr. Fred Sarazin to Lunch Bunch. Fred?
Thank you very much. Well, thank you for the invite to talk at this Lunch Bunch. I was asked to introduce myself, so I'm going to do that now. So indeed, I'm the Department Head of Physics. I'm also, as of March 1st, the Director of Quantum here at Minds. So ever since I've been asking to give a couple of talks already. So this is talk number 3 on the topic. I've been at Minds 21 years. My background is actually in subatomic physics, so originally in nuclear physics, and then astroparticle physics, cosmic rays. I was yesterday at the showcase because I'm also a co-founder of a startup which aims to treat skin cancer, non-melanoma skin cancer with a radioactive skin patch. So I've got broad interests, and quantum is not quite new to me, but I've talked some aspect of it, but this type of quantum is something that I had to think a little bit about before presenting it to you. So I'm going to get started, let's start with a disclaimer here. I'm just going to give you a little bit of a warning of what's coming. So I hope you're going to be able to hear this. This is a kind of a short video that I took out of the PBS NOVA program on quantum, which I really recommend. It's very, very well done. So here's the disclaimer.
The following NOVA program contains scenes of quantum physics, which is known to cause confusion, anxiety, and even heartbreak. Please see your physicist if symptoms persist.
All right, so this is one of those cases in which I can say that I am that kind of doctor. So I don't know very much about heartbreak with quantum physics, but I can tell you that many students, engineering physics students or graduate students in physics have felt the anxiety before taking a test in quantum mechanics. And I will say in terms of confusion that if you're not confused by quantum mechanics, you definitely don't understand it. So that would be my disclaimer. All right, so let's get started now. So as it turns out, quantum mechanics powers many applications, and it's pretty much everything you can think of that is high tech. So here you've got a chip, you have a clock, you have a laser, a fluorescent light bulb, you have an MRI machine, and you even have a toaster here. And all of that actually relates one way or another to quantum mechanics, solid state physics, atomic physics, semiconductor physics, black body radiation, spins, you name it. And let me give you another example here. If you see me on camera, your phone, your smartphone is a marvel of quantum mechanics. You know, it's a GPS receiver. It's got chips in there. It's got a screen. It's got a camera. All of that is powered by quantum mechanics one way or another. All right. So what is quantum in this particular case, right? You've heard a lot about quantum and how minds is involved in quantum, but I will tell you, quantum mechanics is about 100 years old. So why now? So quantum really, as we understand it now, is actually short for quantum information science and technology. And it's going to be based on the same fundamental principle of quantum mechanics of all those other applications, but it will have to do with the spookiest of the spookiest of quantum mechanics. So using interference, superposition, and entanglement on a small collection of atoms, molecules, atoms in lattices, and so on. And those next generation applications in the areas of quantum sensors, quantum computing, quantum communication, quantum materials are going to be based specifically on those kind of spookiest phenomenon in quantum mechanics. And this will likely lead to a new quantum revolution. And the magnitude of this revolution is probably going to be related to how well we're going to be able to do quantum computers. So I'll mention all of this and more in a few minutes. But I will say also that it has some very significant geostrategic implications. Quantum sensors have, security-related aspects, and quantum computers are going to be able to accelerate discoveries. It can break encryptions. So from that perspective, it's really something that is really critical for the United States to to lead, essentially. And as of today, I believe that China is basically outspending the United States about 5 to 1, $5 to $1. So it's really important that we are present here. So here's the fun part for me. I'm going to give you a little bit of a quantum mechanics 101. I do believe this is important because if we talk about quantum, I can go directly to the application, tell you how nice those are, how groundbreaking they are. But the next time you hear about this, you won't have learned anything new. So it's ambitious, right? But what I want to do is I want to give you a sense of what those spooky quantum mechanical concepts are and how they are somehow like non-intuitive, but so important for what we're going to be talking about. All right, so let's start. So here's a picture here that you can, let's start by saying that those are water waves. So imagine that you have a wave of water that is coming from left to right, and it's about to get, it gets into a dam, and there are two openings in the dam, and out of that you get basically two circular waves that are propagating from those openings. And as you can see here, those ripples, they are going to add up, or they're going to, well, they're going to add up together. And sometime a crest is going to meet a trough, and sometime a crest is going to meet another crest. And so what you have here is actually a phenomenon called interference. And you might see destructive interference when the trough meets the crest, and a constructive interference where you have two crests meeting and you get a larger wave. So as it turns out, light is understood. Light is understood also as a wave since about the 17th century. And so you can imagine exactly the same thing here. You have a light wave coming from the left, and now the light is propagating through two slits, creating wavelets that are same thing, moving kind of as a circular wave and interfere with one another. And so if you were to have a screen on the right-hand side here, what you would see is bright fringes that correspond to constructive interference and dark fringes that correspond to destructive interference. Okay, but at the beginning of the 20th century, Albert Einstein was able to explain the photoelectric effect, which is effectively how light is being converted into electricity in solar panels. And in order to explain this phenomenon, you cannot use light as a wave. You have to consider that light acts as tiny particles called photons. And those photons impinges on the material. They basically interact directly with the electrons, and the electrons are kicked out of the material, become free electrons, and that's what creates the current that eventually produces the electricity out of the solar panel. So you see what's going on here. On the one end, you have light as a wave, and you have light as a particle. And the question is like, well, when is light behaving as a particle and when is light behaving as a wave? So let's go back to our little cartoon here. So you have a light bulb, right? That is a light wave coming to the two slits. So this is the so-called double slit experiment. It goes to our two slits here, create those wavelets. Those wavelets interfere with one another. And on a nearby screen, you're going to observe bright fringes, constructive interference, and dark fringes, which are destructive interference. So let me ask you a question now. What if I'm replacing my light bulb with a device that is producing only one photon at the time? So the reason why I'm saying that is because here it's very clear that you have a wave coming in, going through both slits at the same time, recombining and creating an interference pattern. But what if I'm using only single photon? If I send a single photon, you'd think that the photon will either go through the top slit or the bottom slit, and there is no way that it would interfere with itself in order to create an interference pattern. So let's do the experiment. So here is the results of what you will see on the screen after 20 photons. And again, I want to reemphasize here that that tiny speck of light that you see on the screen is indeed the results of a photon interacting in the screen, tiny speck of light. So this is 20 photons, 100 photons, 500 photons, and 4,000 photons. So what you see here is actually an interference pattern. What you would have expected is basically a shadowing of the two slits on the screen. So you would have seen two bright fringes that correspond to the two slits. But in reality, you see an interference pattern as if the photon actually traveled through the system as a wave. And so this is very fundamental to quantum mechanics. And this is indeed how we describe the photon as it travels from the left to the right. And we call that the wave function. Now, the wave function is a very, very strange animal. This is not something that you can actually physically measure. And if you square the wave function, you end up with a density probability. And this is where you've heard already that basically in quantum mechanics, everything is about probability. So if you replay this kind of like the photons moving from left to right here, you have a certain probability of the photon being at a particular, landing at a particular location on the screen. And this is driven by the wave function. But of course, it means also that the photon went through both slits at the same time. So it's a bit of a misnomer to have assumed that it was a particle that actually went through only one slit. it's actually the photon, until we measure it on the screen, did behave actually like a wave. So I hope you're not lost there, because there's more coming. All right, so let's have a little quiz already. So this is a picture that I showed, right, with a regular light bulb producing two waves that interfere with one another, producing bright and dark fringes. All right, so here is my device now. You see my light bulb has been replaced by a tiny laser, but in fact, it's just a device that emits one photon at a time. And so now I'm going to block the top slit. I'm entirely going to block the top slit. So my question to you is that, am I going to observe an interference or not? So for those that are courageous, I suggest you use the chat and you tell me if you think that there is interference or not. And I'll wait a few seconds. All right, I've got one person that says there still would be an interference. Anyone else? Okay, we have very shy people out there, or they're all asleep already. All right, the answer is there are no interferences. And the reason why there are no interferences is because, well, basically I blocked the slit. So now my photon had only one chance. It had only one path to get there, and is to go through the bottom slit, right? So this was a bit of a trick question, right? And someone actually got the exact right answer. All right, so let's do it again. So now I'm not blocking the top slit, and I'm going to put a detector that is going to play a role a little later, but for now that detector is turned off. But that detector is going to basically check if the photon made it through the top slit. So that detector is able to see the photon going through the top slit, and of course will miss all the photons that goes through the bottom slit. Okay, but that detector is turned off right now. So my question is, are we going to see interference or not? I'll wait a few seconds. I got a private message. So that's someone that didn't want to share their answer with everyone. That's funny. Okay. So I think the couple of people that responded, including one privately, was yes, there is interference. And the answer is yes, there is interference, because the detector plays no role. And basically we're in a situation that we were before. So we had two slits open, a single photon, the wave function, basically describing the whole process. We see an interference. All right, so now I'm going to turn on the detector. So now if I turn on the detector, that means that my detector is actively going to be looking for a photon going through the top slit. So my question to you is that, am I going to see interference or not? And I think you can guess the answer to that one. All right, couple more seconds. Some people think that there will be interference. And the answer is no, there won't be any interference anymore, because the measurements that we made actually affected the outcome. So now this is, if you're confused, that's completely normal, right? Because you'd think that turning on a detector has basically no impact on the measurements itself. In reality, that is not the case. And that's a very, very important, another very important concept in quantum mechanics. So think about the way you see me right now on the screen. The reason why you see me on the screen is because there's ambient light here that is basically either scattering off myself or basically interacting with me, and I kind of shine some light to the camera and you can see me. But what if I turn off all the lights? If we're in darkness, you won't see me anymore. Well, that's because even if you think about your eyes as a passive receiver, there's been an exchange of energy between the ambient light and myself for me to be able to send you that signal, right? So, of course, I'm not really affected by this ambient light, but here we're talking about a microscopic photon. And as it turns out, the act of observing the photon going through the top slit, and by definition, not going through the bottom slit, is going to require so much energy that it will affect the photon coming through the slit and destroy the interference. So a very, very important concept of quantum mechanics is that if you're designing your experiment, as we just did here, to detect a photon, light as a particle, light as a photon, we're going to reveal the nature of the light as a particle, and therefore we can no longer see its behavior as a wave. That's another very important concept in quantum mechanics. And in fact, if you think about the screen here, the screen is pretty much designed to detect the light as a photon. And that's why it appears as a photon on the screen. All right, so let's put this together. Here is how we would describe the process in quantum mechanics. So like I said, you have to encode with the wave function, basically the photon going through slit 1 and the photon going through slit 2. So you can write that the wave function is basically a superposition of a wave that is originating from slit 1 and a wave that originates from slit 2. And in this wave function here, we've encoded the interference pattern. So here's the interesting part about this, the wave function basically collapses when the photon arrives on the screen. So it's kind of a little strange as well, because you have a wave that is basically non-local, comes to the screen there, and you could say, well, the wave is everywhere, right? So it should basically hit the screen at all places. But once you make the measurement, that wave function collapses into a single measurement on the screen, and that's that tiny speck of light here. And yet, as I said before, the quantum superposition has basically that wave function that I wrote here has actually encoded the entire interference pattern, right? So keep that in mind when I'm going to be talking about quantum computers. That's something that I'm going to bring back at some point. All right, so the last kind of spooky phenomenon that comes from quantum mechanics is so-called quantum entanglement. And it's, in principle, this is kind of by far the one that is the most complicated to explain. And so I'm going to take a little bit of a shortcut. So quantum entanglement is kind of a special connection that you create between two particles that are produced at the same time, and they would have correlated properties, whether it's their spin, their polarization, those kind of things. So let's move directly to a classical example here. Let's assume that you have two magic coins, and those magic coins, they're correlated with one another. So if you end up flipping one and you get head, the other one, if you're ever going to flip it, the other one is always going to give you tail. Or you're going to flip one and it's going to say head, and then the other one is designed so that it's going to give you exactly the same measurement. So it's in both cases, they're correlated. Either if you do head, the other one will do tail, or you do head, the other one does head, right? But in both cases, you can predict basically what the measurement is going to be with one based on the measurements that you're going to do with your own magic coin. And this has been demonstrated in quantum mechanics, and it's been done over pretty long distances. So classical example again, I give the coin to someone in the audience and they travel to Los Angeles, and I take the coin and I go to New York. And if those coins have not been affected by their surrounding, the person that is going to flip the coin in Los Angeles will find it to be head, for example, and mine will be tail every single time. For any collection of coins, there will always be a correlation between the two coins. So in quantum information science and technology, entangled states are going to allow us to do a lot of different things. One is that it's going to allow us to do operations across quantum objects, and that's going to be important for the qubits. And qubits are quantum bits for quantum computers. It can create new unbreakable encryption algorithms, and it can even allow for networking via quantum teleportation. And if this sounds futuristic and everything, I tell you, this is close to becoming a reality. So I won't talk very much about this anymore. And since this is being recorded here, you can pause the video here and take a look at that little cartoon which I found online. All right, so I'm going to switch to my next topic here, and I'm wondering I can maybe entertain a couple of questions before moving forward. If you have some pressing questions about quantum mechanics, I know it's probably a lot to take at once, and that's why there is a recording. Did I lose everyone? Let me see how many people did I lose here. Am I seeing how many people there are still? 5 people left?
I see 56 people are still on with us.
All
So
right, okay.
yeah, you're good. I think we're all just trying to digest everything you said.
You're trying to process that. Now, I understand. I mean, I understand. The two-slit experiment is actually one of the simplest experiments that you can use to explain quantum mechanics. But yeah, it takes a little bit of digesting, like someone put on the chat. So, all right. Well, let me keep moving, and at least with the quantum computing aspect, I'll bring back this concept of superposition into focus a little bit. All right, so let's talk about quantum sensing. I'm going to go fairly quickly there because there are so many different cases that you cannot treat them all. So the idea is, well, how do quantum sensors work? Well, so those quantum sensors, again, they're going to use those very unique properties of quantum mechanics to measure physical quantities with very, very high precision and sensitivity. Compared to the stuff that we have as applications, like in our phones, for example, it's going to rely on very, very microscopic quantum systems, such as atoms, molecules, collection of atoms, collection of molecules. So those things exist already in the lab, and they're not yet, not many of them are kind of available as regular quantum sensor just yet. So the point is that they're very, very small. And because they're very, very small, a small change of, let's say, magnetic field, electric field, temperature, gravity forces will result in a pretty significant disturbance of those atoms and molecules. And so this allows us to actually detect extremely weak signals. And another benefit of this is that they are so-called self-calibrating. So let me give you a little bit of an analogy here. If you think about a mechanical scale, for example, you know that once in a while you need to kind of reset the zero. And that's because, it's made of mechanical parts, and those mechanical parts, they kind of age. And so once in a while you kind of have to reset the zero, and you're hoping that, they're still going to respond linearly to whatever measurements you're making. In the case of the quantum sensor, they relies on the fundamental laws of nature, on fundamental constants. And so their response is always the same. And because they're always the same, they're called self-calibrating. So I'll give you 2 examples here. So you can use optical traps, for example, to measure very precisely time and motion. And it basically uses a collection of isolated atoms that are going to respond to known frequency of electromagnetic radiation, whether they're being absorbed or emitted by those atoms. And this is what gives us the ultra-high precision time that we use as GPS receiver for our phones, right? Another one, which is a bit of a mouthful, is nitrogen vacancy centers in diamond. And I'm not going to explain why they work this way, but how they work, but they're basically able to detect minute changes in magnetic field with very, very high precision. So I'll give you two examples about those. The first one is GPS denied environments. So among all of those, I'll pick just one. I'll pick mines and caves, right? So if you're in a cave, you don't have a line of sight with any satellites, obviously. So you cannot use GPS to find out where you are. You have to rely on other quantities. Well, if you can measure very precisely the magnetic fields around you, generated by the iron content in the ore throughout the cave, then you can use those tiny, tiny, tiny changes of magnetic field that are generated by the ore in order to move inside the cave. So you can do that because you have a map already of the cave in terms of like its magnetic field signature. Or you can actually do this as you go and you discover inside the mine, as long as you've got some other inertial sensors. Another application might be in healthcare, right? So your heart is basically a pump that uses electric signal to open and close valves. So in physics, electricity and magnetism is about the same thing. So if your heart is operating as with electrical current, it will generate a magnetic field. And so if we have those detectors that are able to very, very precisely measure magnetic field, you can actually do functional imaging of the heart. So this is really cool, and this is really around the corner. All right, so let's talk about quantum computing now, and I'm watching the time a little bit. Let's talk about quantum computing, because this is really at the heart of what the new quantum revolution might be. So let me start with a very popular video that it kind of illustrates the power of quantum computing. So let's start. This is basically what I'm going to show you here is a maze, and then how a classical computer, like a regular computer, would try to find its way out of the maze, right? So what it basically does is what you would do is that you would explore basically every possible path until you find the exit, and you would have to turn around, go back where you are in a dead end, and you do it again until you find your way out. Now, this is very slow, of course. Your computer would have absolutely no problem finding the exit of this maze. But if the maze is big enough, at some point, it's just going to take a very long time. Now, a quantum computer will be able to explore all the paths at once until it finds the exit. So I presume you understand why this would be so much more powerful. And now I can tell you that you can understand this based on the double slit experiment that I explained earlier. Because if you think about it, in the double slit experiment, you have basically a wave that is exploring the top slit and the bottom slit at the same time, induce an interference pattern. But, in effect, right, the slit compared to the photon, the wave compared to the photon is able to explore both slits at the same time. So a quantum computer, that's at the basis of how a quantum computer works, is you basically use superposition in order to be able to explore those paths. So how does this work in practice, right? So for a classical bit, right, for a classical computer, you have a classical bit that is basically registering a value of 0 or 1. So let's say for our maze, it's going to be 0 is right and 1 is left. For a qubit, it's basically a superposition of two states, one that is called a state 0 and a state 1. And the qubit is basically a quantum superposition of both at the same time, right? Actually, let's make sure that we understand this. When we make a measurement, that qubit is either going to register, once you're going to measure this qubit, you're going to measure either a 0 or 1. It's not like you're measuring other quantities. At the end of the day, the value will collapse to a 0 or to a 1. But the the strength of quantum computer is to be able to code both of those at the same time and be able to do some spooky operations between them. All right, so if you think about the maze now, and you assume that your zeros and your ones are basically turning right and turning left, then you can see how a quantum computer would basically go through the maze. So if I've got one qubit, right, I can write the wave function as a superposition of turning right and turning left. If I've got two qubits that are entangled, they can create a wave function that contains now two steps: right, 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 left, left, right, left, left, right? So with two qubits, I'm doing the equivalent work of 4 regular bits, right? Now, of course, if I've got 3, right, if you continue along those lines, if you have 3 qubits, you can actually get 8 different combinations. If you have 4 qubits, you're going to get 16 different combinations. So at the end of the day, if you have n qubits, you're going to get 2 to the power of n classic bits. So it's an exponential growth. So again, if we're looking at the tiny maze that we've got here, a regular computer would have absolutely no problem doing this. And you wouldn't need a quantum computer for this. But let's take a picture take a look at on the right-hand side here. This is a complex molecule that is made of about 41 atoms. So in physics, the many-body problem is really complex and requires some very, very intensive calculations. And in fact, here it is calculated that if you want to explore the phase space of a 41-atom molecule, it's going to require you 10 to the 86 bits. So that's 1 with 86 zeros. And that's basically more bits required than there are atoms in the entire observable universe. Because of the 2 to the power of n for qubits, you can do that calculation with 286 qubits. And if you were to compare that to classic bits again, that's basically the number of bits that you need to manage 1 pixel on your laptop screen, right? But in this case, it would allow you to make calculations that go well beyond what a regular computer would do, period, right? No matter how fast your computer is going to be, it's never going to beat a quantum computer past a certain time. So I'll give you, so those are the calculation for which a quantum computer would be extremely good. You do not want a quantum computer for your Excel spreadsheet. You don't want a quantum computer to play Minecraft. You want quantum computers to do those very, very complex, very, very intensive calculations. Okay, so let me continue here and tell you that there is this tiny little thing there that is written that says that the 286 qubits must be of high quality. And it says that today's qubits have limitation in error rate, coherence, interaction, and so on. Well, that's because you need to be able to generate this very, very, very complex wave function that would have 286 qubits combined, right? And any kind of interaction with their surrounding could actually break that bond that they've got between one another. And then, that calculation will effectively break down. So we need to be able to isolate those qubits from the rest of from their environment so that they can interact with one another. And this is extremely, extremely, extremely difficult. This being said, quantum computing is pretty much on track to create already about $850 billion of economic value by 2040. And it's going to be potentially well in the trillions of dollars. And how many qubits we're going to be able to operate might just drive, all the future discoveries in the world, literally. And so there are going to be countries that are going to have quantum computers and countries that are not going to have quantum computers. And it's going to be almost as simple as that if it comes to kind of their full potential. So here is a picture that shows a quantum computer, and it might be a little confusing to most of you that the the quantum computers is probably somewhere down there, right? The rest here is basically a fridge. What you're doing is you're bringing that sets of qubits very close to the absolute zero in order to avoid the thermal noise that would prevent those qubits from working with one another because they would be disturbed by their environment. And so when you see this nice picture here, all those gold wires and everything, all of that is basically just a fridge. The quantum computers is probably this tiny thing here behind this kind of like, it looks like a silvery cylinder of sort. All right, so we're getting to the third part of my talk, and we've got about 15 minutes left, so I'll have to speed this up a little bit. And I realize that I spent quite a bit of time explaining those two first, in those two first parts, but I think it was really important that as you're going to hear more about quantum here at Minds, that you know where all of that comes from. That was part of my job for this first lunch bunch. And let's say if you want to know more, there'll always be an opportunity for me to come back and tell you about all the stuff that are now happening at Minds around quantum as it progresses, literally. All right, so let's do a short dive into all this here. So the first thing that I want to show you is the CO here. If you remember how I expressed the wave function, I basically expressed it just like that. In quantum mechanics, it's called a ket. And that's because the entire thing that I showed that reads as Minds CO is called a bracket, right? So this ket here is supposed to represent a wave function. And so you see it's a little bit of a play on word here to say that Colorado, CO, is the quantum state, right? So we want Colorado to be the quantum state, the state where quantum happens, right? So it's as much as a play on word that a physicist can do and remain serious. Now, as it turns out, the bracket Minds CO in quantum speak almost literally means Minds quantum contribution to Colorado. And that's why I picked it as the logo for Quantum at Minds. So now you've got like the inside joke of the whole thing. So you can impress your friends. As it turns out, the Quantum at Minds ecosystem is very, very rich here. And I'm not going to go through all of those here, but I will say that, it's at Quantum at Minds is basically at the intersection of research and technology, workforce development, and innovation and policies. And we are strong in all of those areas. So just to show you how much it is here, I'm overlaying here the must-do strategic effort that were presented by President Johnson for Beyond Minds at 150. And so again, I'm not going to go through all of those. I'll pick a few just to give you a flavor of what we're up to. I will point out for Quantum at Minds the moonshot, right? Quantum at Minds is one of those moonshot here that's one of the moonshot that we're going to go after in the next decade or so here at Minds. Okay. So let me highlight just a few here. So the first one is that we've got this incredible opportunity to supercharge our efforts because of Elevate Quantum. So what is Elevate Quantum? Well, Elevate Quantum is the nation's quantum technology hub in Colorado. It started as a consortium of industry partners, higher education, state and local government, economic development organization. And they basically put together a proposal to get an economic development administration grants and EDA grants. And Colorado and Elevate Quantum basically got Colorado to become the only quantum tech hub in the nation. So the funding is about $40 million of federal award, and then it's been matched at the level of about $74 million by the state of Colorado, with the federal dollars for equipment and programming and the state dollars for infrastructure and loan backing. And so the idea of Elevate Quantum is to try to supercharge innovation and bring basically quantum innovations to industry. And so for some of you, you might know this picture here. It's basically a plot of the TRL, the technology readiness level, as a function of investment. And so, the idea starts in academia and it ends up in industry, but somewhere in the middle, there is a gap there that is called the valley of death. And a lot of startups basically die in the valley of death. And so the question is, how do you bridge that? And I will say that Minds, because of its E&I system, its entrepreneurship and innovation system, the fact that we've got this, focus only in engineering, and we've got this very, very strong hands-on training, is probably just getting us closer to industry than a regular academic organization. Nevertheless, Minds, CU, CSU, I've been partner with Elevate Quantum and basically developed 2 different facilities to help with supercharging the economy in quantum. So one is a quantum incubator in Boulder, and the other one is something that you've heard probably already, Quantum Commons at Arvada. And the objective here is basically to bridge that gap in the valley of death, helping companies that basically have good ideas, have access to very, very expensive pieces of equipment, and not die in this valley of death where the investment is just too high compared to what is needed in order to bring things to industry. So another point that I would like to mention here very briefly is the fact that Minds has some very, very unique capabilities and facilities. And it's really surprising to me as a physicist that I never thought that the fact that Minds own a mine, the Edgar Experimental Mine, could be so unique for the stuff that we would want to do. And as it turns out, building quantum labs underground make a lot of sense because those quantum sensors, those qubits, as I said, they're very sensitive to their environment. And so if you build a quantum lab underground, you can shield yourself from electromagnetic radiations that you have everywhere on the surface. You also shield yourself from cosmic rays, which are actually disrupting chips on a fairly regular basis. And so what we're doing here with the Edgar Mine is that we're actually building a lab, a quantum lab, probably the first of its kind, at least in Colorado, to basically study quantum sensors and quantum chips. So here is a picture of the Edgar Mine. You enter from the right-hand side here, the top right. And if you walk through the Miami Tunnel here and you get to the very, very end of the line here, you have this area in blue here called Curie, that is Colorado Underground Research Institute. And this is where we're going to start building quantum labs. The first one of those is just right here, is next to the E of Curie here. And we have a very proud new faculty member in physics that we recruited out of MIT, that is going to have his lab here inside the Edgar Mine. And the reason why we were able to attract him is precisely because we could build him a lab in the mine. All right, so let me finish up here. You may have heard that Minds as the first, one of the first graduate in quantum engineering program in the nation. And this is really important from a standpoint of workforce development, right? The reason why Elevate Quantum exists is also because Colorado has one of the highest concentration of quantum companies in the nation. And so they're going to need people. And so workforce development is really critical. And workforce development is not only master's degree and PhDs. We need to develop that workforce, that quantum workforce at all levels. And so we're looking right now to see if it makes sense for us to create a bachelor's degree with a very strong quantum flavor. And then we may also have the opportunity to partner with the community college for 2-year degrees because those are going to be needed as well. I've seen a picture from Elevate Quantum where they show how you build a dilution fridge. That's basically the fridge that has the quantum computer at the bottom here. And, you know, depending on what you need to do here, you need people that have kind of community college-like training, bachelor's degree, master's degree, all the way down to the PhD. So there are some opportunities here. And then because our students are actually so good and they're going to be, they may have the opportunity to interact through capstone projects with the quantum companies nearby, they may actually get some really good ideas and eventually want to spin off their own companies. And so this is why the E&I ecosystem, entrepreneurship and innovation ecosystem at Minds may play such a big role. All right, and finally, I cannot finish without mentioning Quantum Commons. Quantum Commons is basically a quantum research park, and it's a massive investment from Minds, which is to basically create the equivalent of the Stanford Research Park that basically was the seed for Silicon Valley in California. So really the ambition, you know, the view here is to see whether we can create the equivalent of the Stanford Research Park for quantum in Colorado. And so this one, we're going to have to see 10 years from now how it worked out. But you might be just at the beginning of something really, really exciting here. So let me just show you what the site looks like. This is Arvada here. This is Highway 72. Highway 93 is coming like this way here. This is Golden over there. And behind us is the Flatirons. So the idea is to create the equivalent of a Stanford Research Park for quantum. It's about 70 acres. It's owned, developed, and operated by Minds, to be operated by Minds. It contains a number of buildings that exist already, but that need to be refurbished. And there are some places for future development phases. And that includes actually bringing existing companies to build their facilities here in the park. So this is a work in progress. The labs need to be refurbished. There's going to be a clean room that is going to be built there with funds from the state of Colorado. And so once this infrastructure is in place, we're hoping that this is what is going to attract all the quantum companies. And so maybe one day you'll see an IBM, you'll see an Amazon, you'll see Microsoft, you'll see Intel having kind of a quantum operation, their quantum headquarters in this research park here. So this is really, really exciting. All right, so I'll finish. Yeah, I'm just right on time, I guess. So this is the vision, at least the short-term vision here. I think we have an incredible role to play in workforce development. We've got incredible opportunities in terms of strategic partnership, both with industry and the nearby national laboratories, capitalizing on all our expertise, the fact that we've got Quantum Commons, the fact that we have that we're developing quantum labs in the mine. And so we need to figure out how to do this best. But like I said, those are so distinctive to Minds, to Colorado, to quantum, that we are in this incredible position to aim high and deliver value and maybe make Minds at the end the Stanford of quantum. And that's what I can hope for. And I'll thank you very much.
Thank you so much, Dr. Sarrazin. Wow, I'm still trying to wrap my brain around so much of this, as I'm sure many of you on the call are. Unbelievable. I do see a question from Paul in the chat. Can you all see that? Can you see that?
Yep.
Okay. I will read the question then. Is the Quantum Commons clean room specifically designed only for photonic integrated circuits? Are there plans for tools for superconducting qubits, semiconductor spin qubits?
Wow, I mean, Paul is an engineering physics alum and one of our best. So this is not exactly the run-of-the-mill type questions. I would say at the moment it's photonic only, but because they're going to buy something like 3 different dilution fridges. They are probably going to be some work on superconducting qubits as well.
Very good. Does anyone else have a question that we could answer quickly before we close out? I know a lot of you have put things in the chat, explaining things, answering questions. It's wonderful. Here's another one. What is happening with grassroots education in the high schools to prepare the foundation for quantum innovation in Colorado?
Yeah, so Farai is also someone that is coming out of physics. Nice to see you. Yeah, I mean, so it's all of this, I would say, here at Minds is a bit of a work in progress. So, you know, this is, I think, a little bit of the difficulty at the moment is that I'm still department head of physics. You know, quantum, as I see it right now, is like I'm trying to keep up with the things that can be done in order to, let's say, leverage what we do, what we're going to do in the mine, what we're going to do at Quantum Commons. And the educational part right now is something that I believe is really, really important. What I'm working on right now is looking at this bachelor's degree. But I would say that there has to be an integrated efforts that goes to community college and also to high schools. And it is possible. I think it is very possible. We just need to figure out how to do this. And Elevate Quantum has, you know, has dedicated efforts on this. But the more minds is going to be involved in this, the better, I would say. But then it becomes a problem of bandwidth, I would say.
Mm-hmm.
Someone begins to see the light. Well, I love that.
Yay, Gary. I love it. Steve James has a question. Will quantum computing be more or less energy intensive than the conventional processors being applied for AI?
Well, that's a very, very good question. So quantum computers are not necessarily going to take a lot of energy, right? I don't know what like a full-fledged quantum computer is going to look like. You definitely need to have those qubits as cold as you can, at least, you know, unless someone comes up with, you know, there are some qubits that work at room temperature, and that would be really interesting to see if those are the ones that end up being the winners. But in general, I would say that the quantum computers, I think, are going to spend less energy. And AI is really this, you know, you cannot even compare a regular computer to, let's say, a regular operation of a computer with what is being requested due to AI. So there are some fascinating calculations there in terms of the fact that because AI is tapping into those massive data center, they're extremely power intensive. So think about it the next time you use ChatGPT, right? When you ask a question to ChatGPT, you're not doing a regular Google search, right? This is a query that is kind of very power intensive. And so there is this expectation that as we become, you know, as we interrogate AI more and more often, the demand on energy is increasing really, it's going to increase really quickly. And it's not offset by the fact that we make our computers less, more efficient, let's say. But for quantum computers, in principle, the energy is less. That'll be my guess, but someone may contradict me on that. So.
We do need to wrap up. We are at time, but I want to thank you for sharing these links to the documentaries and the books that may shed a little bit, a few more photons on all of us as we learn more about what this means for minds, what this means for our community, what this means for the world. And Gary has a good question. I would ask the same thing. What is the best way for folks to keep up with the progress of all of this? Is there a website, or will you do a town hall, or what's the best way to learn the latest as you go along?
Yeah, so this is a very interesting question. So I'm a strong believer that communication is important. You know, we need to communicate. This is, you know, especially on topics that are, on the one hand, seem to be like completely like so complex that no one wants to actually get in. But if you kind of figure out a way to demystify this, then people are really going to understand why this could lead to a revolution. And the fact that Minds is right in the middle of it, just feel like you're being part of quite an adventure, let's say. So there will be, I'm sure I will have the opportunities to just continue that kind of communication. There is some real work to be done, but I think there are going to be some touch points where, you know, there will be advancement in particular areas where it's going to be really worth communicating that with the broader Minds community. And so that's what I intend to do.
Very good. Well, we will watch for more, listen for more. And of course, we would love to have you come back for Quantum Part 2 at a future Lunch Bunch in the future, this summer, or sorry, this fall, or maybe next spring, when we've got a lot more to boast about and report back on. So thank you so much. Thank you for joining us, everyone. This has been a great session. We will get the recording ready, and as Andy mentioned earlier, we will post it to our Lunch Bunch page on our website, so you can go back and study those slides and understand and look through this information further. So thank you very much. Before we all say goodbye, I want to remind you about our May program. It'll be our last program until the fall. We are going to take summer off, no program for June and July. But for Thursday, May 15th, we are excited to welcome Kirsten Volpe and Terry Hogue, who will come and speak about the USGS program and this enormous building that is right outside my window. All the partnerships, collaborations, programs that are going to be housed there will emanate from there. And as I understand it, will be the largest building on this campus when it is finished in another year or maybe 2 years. We'll find out the scoop on May 15th. So we'll post that program on the Lunch Bunch page soon, and you can sign up for that. Oh, what a great picture. What are we looking at?
So this is just to tell you that quantum mechanics is about 100 years old now. There was this meeting in Belgium, the so-called Solvay conference, and this is basically the picture that is known as the most intelligent picture ever taken.
Ever taken.
29 participants, 17 Nobel Prizes. I'm sure you recognize here Albert Einstein, but there are Marie Curie. You have all the people that basically helped develop quantum mechanics: Erwin Schrödinger, Wolfgang Pauli, Werner Heisenberg, Niels Bohr, Max Planck. They're all here. So yeah, 29 participants, 17 Nobel Prize. And I always like to point out that the only woman on this picture is also the only one that got 2 Nobel Prizes, one in physics and one in chemistry.
And you know, here we are 100 years later. Maybe we're compiling another similar group to take us into the next millennium, right? 100 years from now, people go, oh, there's Dr. Sarrazin, and there's
It's not gonna be
everybody
me.
in the photo. That's incredible. What a great shot. Thank you for sharing that.
You're welcome.
Okay, everybody, we're 5 after. I hope you don't mind staying a few minutes longer. Thank you again. This has been amazing, and I'm so excited to see what's next, and I hope you are too. Have a great day, and go Ore Diggers. We'll see you all soon.